the topic is smoothness rule and the Fibonacci numbers. In the first B.1, the topic reduce problem size by half. So this is a very interesting problem. So let's take a look at this problem. Problem 10, count binary digits. So let me give you the question first. Given a positive decimal integer n, positive, just the usual integer we are using in positive integer n, decimal. Here the reason, because usually we do not say decimal, right? Here the reason I emphasize this decimal here is because we want to change it to binary representation. Yeah. So, for the comparison purpose, so I use that decimal. Then, question, find the number of binary digits in its binary representation. Yeah. So now you can see we switch between two different number systems, decimal system and binary system. Yeah. All right. I think you have the basic knowledge of changing between these two systems. Yeah. Here, I just want to look at the simple, basic number representation for a general system. Oh, yeah. Just let's look at the binary representation. The general representation, we go too far. Yeah. All right. Let's review binary representation. So given n, this is a regular integer decimal system. Yeah. But we can write in this representation. We can find these b numbers, integers, or 0 or 1. So these b, we know 0 or 1. Okay? Yeah. So then you can always find a sequence of b's, to have this expression, the binary representation. In this expression, we know bs, the last one, always say the most significant bit bs, b sub s, cannot be 0. The reason is simple. If it is 0, we just look at the b sub s minus 1, right? Yeah. So that's why we can assume the most significant bit is non-zero. Then it can only be 1. For other bits, we don't know, but this one, we are pretty sure, it is 1. So then the answer, how many bits in this representation we use? S plus 1. From B0 through BS, there are S plus 1 different numbers. Yeah. So that's the answer, right? Yeah. Find S. So the question, given n, we need to find that S. All right, so that's the question. Yeah. It looks pretty simple, right? It looks pretty simple. Yeah. But here, we want to understand this problem completely from different angles. So you will see, I will use 2 videos, this one and the next one. So we will do a lot of work, analysis, lot of steps we will use. Yeah. All right. So when we work, first, let's look at the insight of this problem. The insight is we want to derive some recurrence relation for this problem. Look at the title, reduce problem size by half, right? Reduce the problem size by half. So we want to derive some special recurrence relation. In that recurrence formula, we have that half size problem representation. Yeah. All right. Yeah. Here, use a transformation to change the structure. Yeah. So that's our general rule. When you work on a relatively hard problem, sometimes you do not have idea how to proceed. In that situation, think about, is it possible to do some special transformation on the general formula? So here we have that situation. Yeah. So let me show you how to do it. All right. The general expression is this. Now we want to do some equivalent transformation. The transformation must be equivalent. Or even if not equivalent, so must be derived. Yeah, I mean equivalent. Sometimes we need an equivalent transformation, but sometimes we can, do a little less than that. Yeah, because equivalent, that's two direction, right? Two direction. You can go this way. You can also go the opposite way, right? But sometimes we only need one way. Okay, one way, one direction. So not necessarily equivalent, but derived from that formula. So for this question, we need one way, not equivalent. So this case, we need one way. Yeah, so what kind of one-way transformation? Division operation. So when you do division operation, integer division. So this division, it's an integer division. Because when you do integer division, you drop the remainder, right? You drop remainder. When you drop remainder, that's one way change, because you cannot go back. When you go back, the dropped remainder cannot be recovered. Right? How can you, after you drop the remainder, you do not store it anywhere. So you do not store it when we drop the remainder. But when you want to go back to the original formula, you couldn't recover the remainder. So that's why we say that's the one-way formula change. But it's okay. That's enough for us. All right, so the division. Left-hand side, because the integer division, it must be another integer, right? So we take the floor function, n over 2 floor function. So the right-hand side, you can see the B0 part is gone, because that corresponds to the remainder part. Remainder. The other terms, they are multiple of 2. So you just do base 2 division, right? Divisor 2 division. Yeah. So here you get a new formula. Yeah. With this new formula, so you can see, all right, so we have a subproblem, right? The problem size is this. Right? All right. So if you solve the problem of this new size, how many bits do you use? S, right? S from B1 through BS, S bits. So you compare S bits answer and the previous answer, S plus 1. The difference is just 1. Okay? You reduce the problem size by half. Here, you reduce the problem size by half, but the number of bits is reduced just by 1. That's the key observation we have. So with that, we get this important observation. First, the least significant bit is removed. B0, so that part is removed. Drop it, remainder. Yeah. Second, the number of bits is reduced by 1. In our binary representation, the number of bits reduced by 1. Yeah. The third one, the problem size is reduced by half. So we put all these things together, we get a recurrence relation. Yeah, so that is this. So we just give a function number. So here we call a special function number. Yeah. Being rec of n, the problem size n, equals the number of bits. So for this function, it returns the number of bits used for binary representation for number n. All right, so equals the problem size reduced by half, the same function recurrence call, then, because the difference is 1, so we need to add 1 number back to it. The two sides are equal. That is our recurrence relation. But we need a base condition. That is this. So when you have represent integer 1 bit. Yeah, that's the answer, 1 bit. Yeah. All right, so we derive this recurrence equation. The next thing, we solve it. We just need to solve it. Yeah. To solve it, we will do two different ways. The first way, write a program to calculate the answer. Yeah. Here, I put a pseudo code to calculate the answer. Yeah. So this is the pseudo code. Yeah. All right. So the main case, return recurrence function call plus 1, right? Yeah. Recurrence function call. Yeah. We solve it. We get the answer. Yeah. All right. Yeah. So you can see it's pretty easy. Yeah. All right. But we also want to look at another way. Yeah. Not in the program. We want to find the formula mathematically. Is it possible we can find mathematical representation of the function, recurrence function? If we can, that's the best. Yeah. But sometimes if the problem is relatively hard, we may not be able to do that. Fortunately, for this question, we can do that. So that's the reason we just do it. Yeah. All right, so next, we want to solve this recurrence relation. Solve this problem. Okay? So we solve it. Yeah. You can see mathematically, it is not trivial. When you try to solve it, it is not trivial. Yeah. So that's why we need some special technique. When we solve it, here I can use different strategies, different techniques, different tools, to help you, learn new methods. Yeah. So that's the purpose. Yeah. All right. So let's look at the analysis part. All right. So here, yeah. Before I do the analysis, I want to point this out. Division, right? N divided by 2. Although on paper it is a division operation, but actually it is a left shift operation. You shift decimal point, not decimal point. Here, because the point, you need to consider the binary. The point in the binary representation, right? In computer, you use the binary representation. You do divided by 4, or 2, yeah. You shift that binary point one position to the left. That operation, that is very fast, right? That is much, much faster than the regular division. Regular division, faster than that. Okay? Yeah. Actually, it is even faster than addition. We know addition is pretty fast. But shift operation even faster than addition. Addition, you can think about how many operations you need to do, right? You need to manipulate many digits, right? Yeah. But this one, shift, pretty fast. Internally, really fast. Yeah. So that's why, here, the division is not that bad. Yeah, because usually the division is very slow, but the special shifting operation, it is a really fast, nice operations we want to have. Yeah. All right, so next. Yeah, but here still we treat this plus as the basic operation. Yeah. Because every time when we do the recurrence call, we add 1 to our counter, right? So we need to use a counter. We add 1 to the counter, so that addition, we treat it as the basic operation. At the end, we want to see how many additions do we use to find the answer. Yeah. All right. So now we define an A function as the number of additions. That's our basic operations. We want to count the number of basic operations. So we define a new function for analysis purpose. Yeah. All right. So A of n, recurrence relation. Oh, yes. Just a minute. Yeah, here. Right. Yeah, I found some problem. Yeah. Yeah. Anyway. Yeah. All right. Yeah, because here, A of 1, I use 1. Yeah. A of 1, I use 1. Yeah. It's okay. Yeah, because we add 1 to 0, right? Yeah. We add 1 to 0. Although we do not need, we add 1 to 0. It's okay. Yeah. Yeah. Anyway, yeah. So A of 1 equals 1. Yeah. So it's fine. Yeah. All right. So this is our new recurrence relation. You can see it is basically the same as the original one, but the meaning is different, right? The meaning is different. So it's okay. Yeah. Form the same, meaning is different, but they should have the same final formula. Yeah. All right. Question: how to handle the floor function? Here you can see the sticky part. When we manipulate the formulas, some part is not that friendly to us. The sticky part is the floor function part. Floor function part. Sometimes we need to drop some remainder. Sometimes we do not need. But we don't know. There is some uncertainty there. If you drop any remainder or not, we don't know. That's the uncertainty. But that kind of uncertainty make our manipulation a little harder, right? Yeah. So here we notice that. Yeah. So look at the property here. When n is even, no remainder drop. Well, n over 2. That's pretty straightforward. But n is odd, we need to drop some remainder. So to find the final answer, we need to change a little bit. N minus 1 divided by 2. So we drop that 1 remainder divided by 2. So you can see these two cases we need to handle. Yeah. All right. But when we work on the whole problem, here we use some strategy. We use it several times before. So I hope you still remember. So this simple strategy, pretty effective So we use it several times before. Here, I use it another time. So what's that strategy? Start with a simpler case. Yep, that's natural, right? Because if we work on a general case immediately, it is too hard for us. So we don't have the experience. We don't have, good understanding on the problem. So we feel hard to work on it directly. But working on a simpler case, we can handle. Yeah. So that's the reason. All right, so but here, how do you identify a simpler case, right? There are many ways to define, to choose a simpler case. How do you define or choose a particular simpler case? Yeah, here, let me point that out. What do you wish to have, right? What do you wish to have? Usually you wish to have simpler situation, right? Yeah. So based on basic human nature, people like to have some relatively simpler case to work on, right? Yeah. Although some people like challenging problems, yes, yeah, true. Yeah. But people tend to select simpler problems to work, simpler case to work first, right? First. Yeah. All right. So here we try to select that. What do we wish? Yeah. If you look at this equation, what do we wish? Yeah. One thing we wish is the flow function would not cause problem. That's what we wish, right? You don't wish that flow function causing problem. In what situation the flow function does not cause any problem? When n is even, right? When n is even, the flow function does not cause any problem. But when n is odd, you need to do a little more to make it right, right? You need to do a little more. Yeah. All right. So we choose the easier case first. N even, that's the easier case. So we choose that. We assume n is even. How about that? Yeah. But after n is even, we apply the recurrence relation. We go to the next level, next formula. This time, you need to deal with another sticky flow function, right? Another case again. But this time, can we wish n over 2 also even? So we avoid the, sticky situation, right? Yeah. So we keep assuming every time when we reduce the problem size by half, we assume the original problem size is an even number to be easier for us. Yeah. So if you keep assuming that, at the end, you will have n is power of 2. N is power of 2, right? Yep. Only when n is power of 2, then you can keep doing division by 2, still get integer number. Still, you never need to drop any remainder. Yeah. So that is the best situation we want to have. So with that, someone may argue, how can you assume that? It's too much. This assumption, it is too much. If I go back to the original plan, this is the first case we like to work on, right? It does not mean we only work on this case, right? Later, we will work on the general case, but we need to get some experience at the beginning, right? That's the reason although we make a lot of special assumptions, but we are fine. If later we can cover the general case, then we are fine. Yeah? So don't worry. Yeah, we can do that. Yeah. All right. So next, I want to solve the problem. When n is power of 2, let's solve the problem. Let's find the answer. Okay? Yeah. Because that is the easiest case we can work on at this point. N equals 2 to the kth power. Yeah. So we know k equals log base 2 of n. Yeah. So the new recurrence relation we can write in this way. How about that? In this way. Okay? Yeah. Yeah. All right. Yeah. So then let us try to solve this recurrence relation. Okay? Yeah. All right. So let's do the work. The first time we start with this equation, the next time division by 2, so we get this version, and so on. Okay? Keep doing until we reach the base level. Yeah. All right. Now, after we add up all the equations, we can do a lot of cancellations, left, right, two sides, and finally, after all these cancellations, at the end, we get a of parenthesis 2 to the kth equals how many equations do we have? Remember counting by reference. In module 1, I give you the counting technique, counting by reference. All right? Counting by reference, what's the answer? The number of ones we have, how many ones corresponds to the number of equations, right? So you need to count number of equations. The reference, can we use the exponent number as the reference? 0, 1 through k minus 1. Can we use these numbers as the reference? Count from 0 through k minus 1, that's k, right? K, all right? So you have k equations. So k ones plus the last one, a of is another one. So that's the reason we have k plus 1. So the final answer is this k plus 1. All right. Yeah, so now we want to go back to our result for the special case. A of m, we want to go back to the original problem size, m equals 1 plus log base 2 of n. Yeah. But here, it only works for n equals power of 2. For the non-power of 2 case, we don't know. We don't know the answer. Yeah. All right. But we don't know the answer. Can we guess? Remember, guess and verify strategy we used before. Here, do we have enough information to guess the general case? With this formula, can you make some reasonable guess? Right? Yeah. Here, the general guess we can make. Yeah. A of n equals 1 plus, we know that function, a function, should be an integer. So here, log base 2 of n, not necessary integer, right? Can we take floor function to make it integer, right? Floor function to make it integer, right? Yeah. Yeah. But you may ask me why you do not use the ceiling function to make integer. That's easy. You plug in n equals 1. You can check floor function is correct or floor n equals 1 is okay, right? Yeah. N equals 2, right? Yeah. N equals 2. Yeah. Integer, equals 3. Yeah. N equals 3. N equals 3. Because it's not a power of 2. So you can verify which version is correct. When n equals 3, log base 2, that's 1 point something. Floor function, you get a 1. Yeah. Floor function, you get a 1. 1 plus 1, you get 2, right? Ceiling function, round it up, you get 2, right? Because 1 point something, round it up, you get 2. 2 plus 1, you get 3. But to represent n, remember n, 1, 1. N representation binary, it's 1, 1. Yeah, so you have 2 1s, right? 1 plus 1, you have 2 1s. If you have 2 1s, so this is a better answer, not 3, right? Yeah, in that way, we can fix floor version or ceiling version. So that's a reasonable guess. All right, so we complete our first video. The second video, I need to prove this guess is correct. All right, so let me finish the first one.